Hey, yo, welcome back. On tonight's homework, we're going to be using the calculator for the first time to answer some questions that have to do with the fundamental theorem of calculus. Number one says, given the velocity of an object is given by this function right here, this product of sine and natural log, where v is measured in meters per second, determine each of the following. Remember to show your setups, record 3 decimal places, and indicate units in each answer. The first one, part A, says determine the displacement of the object on the interval 1 to 4. So displacement is this net change in distance, and we can find that by integrating the velocity function from 1 to 4. In other words, we want to find the value of the definite integral from 1 to 4 of that function vt. So you can either write v of t or you can write the entire equation. Either way is fine. I'm going to put the whole thing in there. Okay, and so dt, of course. And so this is something that we're going to put into the calculator, and pretty recently, the AP test has allowed for students to use Desmos, or at least a testing version of Desmos on the calculator portion. And I'm going to highly recommend that that is the platform you are going to use for these calculator problems. If you have a TI-84, that's fine. I'm not going to use that on any of these problems. But if you want some help with using that calculator, you can always come talk to me and I will guide you through how to do this on that calculator. But I think if you do it both ways, you're going to find that Desmos is a heck of a lot easier to use. So you can either follow the link that I have here on the homework. You could scan the QR code, or you could just Google Desmos calculator. Even if you don't go to the testing specific one, I think everything we're going to do is going to be available on both the regular Desmos and the testing Desmos. So let's go ahead and head on over to Desmos. And I've got some stuff in there I'm going to clear out. So the function that we're going to be working with, I'll type that in over here, v of t equals sine of t squared. Oops. Let's get back over there. Sine of t squared. Ooh, look at that graph. That's kind of interesting. Plus 1. Ugh. times the natural log of t. Now, if you try to integrate this by hand, I think you're going to find that that's going to be pretty difficult. Oh, wow. Take a look. This is a pretty wild looking function here. One thing I'm going to do is I'm going to move collapse this y-axis down so we can see it a little better, and maybe spread the x-axis out a little bit so we can kind of see exactly what's going on with this function. Kind of a cool looking function, honestly. So anyway, we want to find the integral from 1 to 4 was what the problem asked for. And we can't really, find it using geometric formulas or anything like that. We're not going to do a series. What we're going to do is just let the calculator compute it for us. So you're going to type the letters INT, and it'll bring up this integral symbol. You can also access the integral symbol by clicking the little keyboard in the bottom left corner here, and you can click functions, and it'll bring up a bunch of commonly used functions. All the calculus stuff is toward the bottom here. And you can see they've got an integral symbol, a derivative symbol, summation, and some other stuff that we don't need. But I think it's just easier to type INT. Nice little shortcut there. So anyway, we're going from 1 to 4. And we don't need to type the whole function again. We could just type v of t. And if you'll notice, it doesn't actually compute it yet. It's giving you a little error. And that's because we need the dt. And there you go. That's our answer. So we have negative 0.065. Now on the AP test, you do need to have 3 decimals of precision. And the thing is, they don't really care if you round or truncate. And by truncate, I mean you just cut off the decimal. So I would recommend that you just, cut off that decimal. Don't bother rounding. There's no advantage to rounding. there's actually a disadvantage in that you might round incorrectly. So do yourself a favor and just write down those 3 decimal places or those 3 digits after the decimal, and don't even look past that. So let's go back to the homework so we can actually record our answer here. And so this is going to approximately equal negative 0.065 meters. So it said that the velocity was measured in meters per second, and therefore the distance or displacement is going to be measured in meters. Okay, part B asks for the total distance traveled by the object on the interval 1 to 4. The difference between distance and displacement is distance doesn't really care about what direction you're going. No matter what direction you're moving, the distance is going to be positive. So like if I'm standing still, if I'm at a position right here and I walk 5 meters over here to position B, and I walk 5 meters back, my total distance is 10 meters. That's how far I traveled. But my displacement would be 0 because I ended up where I started with. My net change in distance would be 0. So the difference between distance and displacement is exactly that. You're just going to add up positive distances, positive values for the distance, and the displacement is going to keep track of what's positive and what's negative. So the way that we're going to actually come up with this total distance is we want to make sure that all the distance or all the change in position that we calculate with this integral is positive. And to do that, we just need to take the absolute value of that velocity function, just to make sure that all those values are going to be positive. So we're going to have the integral, and you can write v of t here, or you can write the full equation. You could write all this, or you can write this. Either way is fine because the function is defined within the problem. And we want the absolute value of that to make sure that we don't get any negative distances. So this is something we'll just go back to Desmos. We're going to calculate that. Let me head back on over there. And so I've already got pretty much everything typed out here already from the last problem. The boundaries are the same. I'm going from 1 to 4. The only thing I need to add are these absolute value bars. So I'm going to put one here, and there you go. So it's going to be 1.585 meters. Now, if I compare that to my answer for A, you can draw a conclusion here that the object was moving back and forth, right? And you can see that in the graph. It seems like pretty obvious. But the fact that these are not the same means that some of this distance that we compute in part B is actually like a negative, you're moving in the negative direction. So I just want to make a quick note of that. Part C says determine the velocity at time equals 2. And is the object moving left or right? So what we need to find is v of 2. That's what we want to compute. And you'll definitely need a calculator for this because if you try to just plug in 2 into the function, you're going to have to calculate sine of 2 squared plus 1, so sine of 5. 5 is not a value that is going to be easy to calculate the sine of. Same thing goes for natural log. So this is why this is in the calculator section. And we've already got v of t, and this is why I kind of like putting the function as like the first line, so you don't have to keep typing that over and over again. Here we can literally just write v of 2. And we get our answer. So same kind of deal here. This would technically round up to negative 0.665. I guess like round down since it's negative, but we're not going to do that. We are just going to truncate. We're going to cut off the decimal after that third digit after the decimal place. So it's going to be negative 0.664. And since this is the velocity, we're going to go with the units that were given in the problem, meters per second. So this is the first half of the problem. The second half of the problem is asking if it's moving left or right, and this has to do with whether or not the velocity is positive or negative. So because the velocity is negative at 2, we know the object is moving to the left. Okay, so it's moving left because the velocity at 2 is negative. The last part wants the acceleration of the object at t equals 4. So here, since we need this acceleration, we need to make a connection between the acceleration and velocity. On the AP test, anytime you're given one of these particle motion functions, whether it be position, velocity, or acceleration, if the question is asking for something they don't give you, you always have to establish that relationship. For example, if you're given position and the question's asking for velocity, you need to say something like velocity is the derivative of position, right? In this case, we're given velocity and it's asking for acceleration. So we need to establish that acceleration is the derivative of velocity. Okay, so make sure you always write that connection anytime you're faced with one of these particle motion questions and they give you like one of the functions and are asking about another. So, okay, we've established that the acceleration is derivative of velocity now. And what we want to know is what is the acceleration at t equals 4? So the acceleration at 4 should be equal to the derivative of the velocity at 4. Now, we don't have to actually find the derivative of that velocity function by hand. That would require both the product rule and chain rule, and it's doable, but you don't have to do that on the calculator section. Instead, you're just going to go back to your calculator. So I'm going to go back to Desmos here, and then just simply type in v prime or v apostrophe of 4. And it should just give you the answer right away. And so, yeah, we get negative 3.292 meters per second squared. Okay, and that takes care of number 1. Let's move on to number 2. It says shampoo drips from a crack in the side of a plastic bottle at a rate modeled by this function y. Now this is a rate. So this is the derivative of some other function. Okay, this function's measured in ounces per minute. And so the antiderivative of this function is going to be in terms of minutes. Okay, so it says if there are 32 ounces in the bottle at time equals 0, how many ounces are left in the bottle after 5 minutes? All right, so let's start here. First, we need to set up this problem, right? We're trying to figure out, now this is this function y is giving you how many ounces per minute are like exiting the bottle. So you have some number of ounces in the bottle, and it tells us we started with 32. Okay, so we have 32 ounces in the bottle, and we're going to take away the net change of the number of ounces that leave the bottle. Okay, and that net change is going to be that integral from, in this case, 0 to 5, because we're going to 5 minutes, of that function y. So there's your setup. You start with the 32 ounces, and then we're going to take away the total number of ounces that exit the bottle. So this is our setup. We're going to go over to Desmos to type in that y function. We're not going to try to deal with that by hand, and we're going to let it calculate this value. Let's go over here. I'm going to just delete all this other stuff. We don't need that anymore. And we're going to call this, I don't know if it's going to like y of t. So I'm just going to call it f of t. Maybe we go back and see if you can actually use y, but I'm not so sure there. So t divided by the square root. You could do sqrt for square root, or just go down here to the keyboard and go over right here. You can click it here, but I like using the shortcuts. sqrt, bring that square root right up. So the square root of 1 plus t to the power of 3/2. So here's the graph of that function. And what we want is the 32 ounces that we start with minus the net change. So minus the integral from 0 to 5 of f of t. Okay, so we get 26.936, or we'll have to go look at our answer choices to see which one's closest to that. 26.936. Let's head on back here. And yeah, we see that's going to be choice A. Okay, so it's going to be approximately 26.93. They ended up rounding up. So, on a multiple choice section, you don't really have a choice. You're just going to go with whatever they give you. Yeah, so there you go. This is choice A, 26.937 ounces. So you started with 32. You subtracted what looks like, about 6 ounces, or maybe even a little bit less than that, like closer to 5 ounces. And that's how much is left. Number 3. Okay, no more calculator. So we're gonna stay off Desmos, I think, from here on out. We're gonna do everything by hand, but I think it'll be doable. So this one says determine the value of the integral of this piecewise function from -1 to 3. So we've got, just to give you a little sketch here as far as what it is we're computing, it says that we're going to use this quadratic function, 3x squared plus 4, for when x is less than 2. So when x is less than 2, we've got this quadratic, just a parabola shifted up 4, y-intercept of 4, and then when we get to x equals 2, we're going to stop. Put an open circle there. The next function, the next piece is 4x minus 5. So that would actually start at -5 with the y-intercept of -5. It would be like somewhere down here. So let me highlight this so we can see exactly which one's which. And then I go up 4 over 1, up 4 over 1. And I'm not really sure if this is going to be above or below. Let's see, at 2, we have 2 squared is 4, times 3 is 12, plus 4 is 16. So yeah, right here is at 16. And then 4 times 2 is 8, minus 5 is 3. Okay, so this is actually going to be like down here, positive slope. Just want to give you a rough sketch on what this graph is going to look like. This is, not to scale or anything, obviously, but hopefully it gives you a good idea of what we're actually trying to find. So basically, we're going to find the area just like we would evaluate this normally using the fundamental theorem, but we need to split it up because the function is defined differently when x is less than 2 versus when x is greater than 2. So if we're going from -1 to 3, we're going to use the parabola, this quadratic function, between -1 and 2. And then after 2, we're going to use the linear piece. All right, so this will equal the integral from -1 to 2, 3x squared plus 4 dx, plus the integral from 2 to 3 of 4x minus 5 dx. So we're going to need to find the antiderivatives of each of these expressions. With that first one, we get x cubed. 3 divided by 3 is 1. So we just get, x cubed plus 4x plus c from -1 to 2. And for the linear piece, we get, let's see, x squared, 4 divided by 2 is 2, so 2x squared minus 5x from 2 to 3. Now I'm going to substitute in 2 and negative 1, subtract those for that first piece, and do the kind of a very similar thing with that second piece. So for the first piece, if I substitute in 2, I'm going to get 8 plus 8 minus, if I substitute in negative 1, I'll get negative 1 minus 4. I'm going to ignore the c's because, as we've seen many times, those c's are going to cancel each other out. And then for the second piece, I'm going to start by substituting in 3. So 3 squared is 9, times 2 is 18. 18 minus 15, 5 times 3 is 15. And then minus, we'll substitute in 2 now. 2 squared is 4, times 2 is 8, and 5 times 2 is 10. Okay, so now we're just going to clean this up and get our final answer here. So we have 16, negative 5, plus 5, plus 3, and then we have 8 minus 10 is negative 2, so plus 2. So we've got 16 plus 5, let's see, 5 and 3 make 8, 8 and 2 is 10, plus 16 gives me 26. All right, number 4. Here we're just doing basically a simpler version of what we did in number 3. We just have a single expression that we need to find the antiderivatives. And then we're going to plug in 2, plug in 0, and use that fundamental theorem to calculate this definite integral. So the antiderivative of 2x cubed plus 3 is going to be 1/2, because 2 divided by 4 reduces to 1/2, times x to the 4th plus 3x. And we're going to go from 0 to 2. So if I substitute in 2, let's see, 2 to the 4th. It's going to be 2 times 2 is 4. So let's see, 2, 4, 8, 16. But I got to multiply that by half, so I'm back down to 8. So that'll be 8 plus 3 times 2 is 6. Minus, and if I plug in 0 here, I'm just going to get 0 and 0. So I can just kind of ignore all that. And so I have 8 plus 16, 8 plus 6, which is 14. So my answer is C. For number 5, we've got another definite integral, but on this one they gave us the answer. So they gave us the total area and did not give us a constant that's sort of embedded in that expression. So what we're going to have to do is set up an equation using that fundamental theorem and solve for k. So the integral from 0 to 2 of this, we need to find that antiderivative. So if we raise that, it's going to be x to the 4th. 2 divided by 4 is 1/2. So 1/2 x to the 4th minus, let's see, k over 3. This can be ugly, times x cubed. Now here, 2k is a constant. So it's just going to be 2k x. And then, of course, we get a plus c. And we're going to go from 0 to 2. And this whole thing's going to equal 12. So what I need to do is substitute in 2 for x, substitute in 0 for x, and then subtract those two expressions. So the first one is going to be 1/2 times 2 to the 4th. We did that back on number 4. So that's just going to be 8 minus, let's see, 2 cubed is 8. So we have 8/3 k plus 2 times 2 is 4, so plus 4k. We know the c's are going to cancel out, so I'm not going to write those. Minus, and here we've got just like everything's going to zero out here because each term has an x. So if I plug in 0 into all those, we're just going to get 0. And that's going to equal 12. So the equation I'm really working with here is 8 minus 8/3 k plus 4k equals 12. So first I'm going to subtract 8 on both sides. 12 minus 8 is 4. Then I need to combine like terms here. So let's see, 4 would be 12 thirds. So 12 minus 8 is 4. So I have negative 4, oh no, positive 4 thirds. K equals 4. Then I'm going to multiply 3 on both sides and get 4k equals 12, and then divide both sides by 4. I'm going to get k equals 3, and our answer is E. Number 6, we want to determine the following definite integral. So we're going to go through basically the same steps we've gone through on a lot of these fundamental theorem problems. But first, we're going to try to rewrite this expression so that it looks more like a polynomial. And so we could use the good old power rule when we try to find the antiderivative. So this will be equivalent to the integral between negative 1 and 1 of x squared over x is just going to be x. And then minus x divided by x is 1. So you get a much simpler expression here to deal with. So this is going to equal the antiderivative, which is 1/2 x squared minus x plus c from negative 1 to 1. If I substitute in 1 here, I'm going to get 1/2 minus 1. And again, the c's cancel out, so I'm not even going to bother writing it. Minus 1/2 plus 1. So this actually works out pretty nicely. We've got 1/2 minus 1/2 is 0. We've got negative 1 minus 1. So this is just going to be negative 2. And our answer is A. Number 7 says, using the table below and the fact that f prime is continuous on the interval 0 to 2, determine the integral from 0 to 2 of f prime x. So we have our good old fundamental theorem of calculus that tells us that the value of this is going to equal the antiderivative of f prime, which is just f, evaluated at 2 minus f evaluated at 0. Now both of those are going to be found in the table. F of 2 is going to be 12. F of 0 is negative 5. So we have minus negative 5, which would be equivalent to adding 5. So this is going to equal 17. And that brings us to our last section here, number 8, where we've got 6 different integral problems to solve. And it looks like some of them are definite integrals and some of them are indefinite integrals. So some of these we'll actually be evaluating using the fundamental theorem, and some of them we're not going to use the fundamental theorem at all. We're just going to find the set of antiderivatives. Now, let's just start with A. Now, on this one, I'm going to start by distributing that x, okay, to make sure that I've got something that's just a little bit easier to work with here. So this is going to be x squared plus 4x dx. And the antiderivative of x squared plus 4x is 1/3 x cubed plus 2x squared plus c. We'll evaluate that from 1 to 2. So first we'll substitute in 2. 2 cubed is 8, so this will be 8/3 plus 2 squared is 4 times 2 is 8. And if I substitute in 1, I'm going to get 1/3 plus 2. So 8/3 minus 1/3 is 7/3. 8 minus 2 is 6. 6 is equivalent to 18/3. And 18 plus 7 is 25. So this is going to equal 25/3. Letter B is an indefinite integral. So all we're going to do here, we're not going to evaluate anything. We're just going to find the family of antiderivatives. So we're just going to anti-differentiate each term separately and then stick on a plus c on the end. We don't want to forget that. And then we'll be done. So the antiderivative of sine is negative cosine. And that's because the derivative of cosine is negative sine. The derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. And these are those derivatives that you just need to know. If you're going to be successful on an AP test, you really got to know those transcendental derivatives. And we'll do more practice with them as the year goes on. Okay, that's it for B. Letter C, we're going to work out just like we did letter A. Actually, it's a little bit easier because we don't have to do any distributive property or anything to set it up. The only thing I want you to look out for is notice that the boundaries are opposites. So this is actually going to equal the opposite of the integral from 1 to 3. Now, if you're going to evaluate this using the fundamental theorem, you actually don't have to worry about that. Okay, you just be careful about what you're going to plug into x here. So let me show you what I mean. We can just sort of ignore the whole negative opposite boundary thing and anti-differentiate 4x squared. That's going to be 2x squared plus 5x plus c. And then I'm just going to go from 3 to 1. So notice that the boundaries, I'm leaving them backwards, but that's going to take care of itself once I start substituting things in. So I'm going to substitute in 1. So that's going to be 2 plus 5. And then substitute in 3. 3 squared is 9. 9 times 2 is 18. 3 times 5 is 15. So I get 7 minus, let's see, what would that be? 33. 33 minus 7 is going to be 26. So it's going to be negative 26. And if you were to have worked this out differently, like if you were to set this up so that it was actually like the opposite or negative 2x squared plus 5x plus c, and then go from 1 to 3, you're going to get that same thing. You're going to get that same value. But that's kind of the nice thing about the fundamental theorem of calculus when we're using it to calculate these definite intervals is it takes care of that for you. Okay, part D. Here we're going from 2 to x, so we've got some unknown variable upper bound here. But we're going to not really think about it any differently than any of these other problems. Honestly, we're just going to go through and work it out like we did A and like we did C. So first we'll anti-differentiate, and so that's going to be t cubed plus 4t from 2 to x, and we're going to substitute in x, and we're going to substitute in 2. So first I'll substitute in x. Get x cubed plus 4x. Oh, I forgot my plus c. It's very easy to kind of forget that because it does just cancel out, but we do need to write that. We need to keep track of that. Okay, so we get x cubed plus 4x minus 2 cubed is 8, and 4 times 2 is 8. So yeah, all we get here is x cubed plus 4x minus 16. And our answer should be in terms of x because the area is going to depend on whatever that upper boundary is. E. Okay, here we got to know what the antiderivative of cosine is. So since the derivative of sine is cosine, the antiderivative of cosine is sine. So this is just going to be 3 times sine x from 0 to pi over 2. So if I substitute in pi over 2, I'm going to get 3 times the sine of pi over 2. Pi over 2 is equivalent to 90 degrees. So it's that very top point on the unit circle that we're thinking about. And the y-coordinate there is 1. So sine of pi over 2 is just 1. And then if we plug in 0, we get sine of 0. Well, that's just 0. So this will just equal 3. Yeah, I guess that bell is the cue for we need to finish this up. All right, F. I'm going to set this up kind of, we did one before that was kind of like this, number 6. where we divided each term in the numerator by that monomial in the denominator, and try to rewrite this, simplify it so that it looks more like a polynomial. So this will be the integral of x cubed plus 3 plus 8 over x, or 8 times x to the negative 1. And this is an indefinite integral, so we don't actually need the fundamental theorem. All we're going to do is find the antiderivative of each one of these terms. That's going to close out our homework. So we're going to raise the exponent to 1, x to the 4th, and that's times 1/4, plus 3x. And it's this last one that you really got to be careful about, 8 times x to the negative 1. Now, the derivative of the natural log of x is 1 over x, or x to the negative 1. But because of the domain restriction that we talked about previously, you can't substitute any negative numbers into natural log. So, but this function here, doesn't necessarily have that same restriction. So to make sure that every x value gives us an output, we need to take the natural log of the absolute value of x here. And we do need a plus c at the end. And that's it. We don't need to substitute anything in because this is just an indefinite integral. And that's going to close it out for this homework. So thanks for watching, y'all. As always, please let me know if you have any questions. But otherwise, y'all have a great day, and I'll see you next time.